Hi and Assalamualaikum everyone. Now that we have done on our regression model in the previous chapter, the next step is to assess how well it fits the data. So this process is known as model adequacy checking. So in this video, I will cover and focus on these two, F-test lack of fit and transformation. So this lack of fit test is important. Let's see if the test is significant. So it suggests us that our model does not fully capture the relationship between the variables, between independent and dependent. And transformation is actually we may need to transform the data if our model have any issues like nonlinearity or heteroscedasticity. So we may need to perform some common transformations such as taking the log or square root. So basically, the lack of fit test is used to evaluate whether our regression model adequately fits the data. So it is used to ascertain whether a linear regression function is a good fit for the data. Don't worry, later we will go into the hypothesis testing for the lack of fit, where we'll try to compare the null hypothesis, which assumes the model fits well against the alternative hypothesis that suggests a lack of fit. We will also go through a practical example to see how this lack of fit works. But before that, we need to understand or we need to know some assumption where the lack of fit test assumes that the observations y for a given x are independent and normally distributed, and the distributions of y should have the same variance. Alright, let's break down the component for the hypothesis testing for the lack of fit test. We will start with the hypothesis. The null hypothesis saying that the model fits the data well, or in other words, meaning that there is no significant lack of fit. And the alternative hypothesis, H null, it tells us that the model does not fit the data well, indicating a significant lack of fit. Alright, and then to perform this test, we will calculate, or we use the f-test lack of fit, where we compare the lack of fit mean square, which actually measures how much the variation remains unexplained by the model, and we compare to the mean of square of pure error, which actually measures the natural variability from the repeated observation. So this mean of square lack of fit, we actually obtain them by calculating the sum of square lack of fit divided by m minus 2. M is actually number of level of the independent variable. And then mean of square of pure error, we obtain it by dividing the sum of square pure error divided by n minus m. This is the number of observations. So this is how you calculate the sum of square pure error. And then we need to obtain the sum of square error first, and then we can have the sum of square lack of fit. Alright, and then the critical value, we can determine it from F distribution based on the degree of freedom for both lack of fit and the pure error. And the significant level, normally we typically set it as 0.05, right? So we will compare our F statistics to the critical value. Let's say our F statistic is greater than critical value, therefore we reject the null hypothesis, indicating a significant lack of fit. And what about if our F statistic is less than the critical value? So meaning that we fail to reject the null hypothesis, so suggesting that the model fits well. Let's go through one example. To perform the lack of fit test, I just read the example here. The following data shows the retail price for 12 randomly selected laptop computers along with their corresponding processor speeds. So our number of observation is 12. So given that we have this value as xy, as xx, as yy. This is actually, we have learned this to calculate all this value when we try to obtain the regression coefficients, the slope in the previous chapter, in the second chapter, I think. So this is actually, for example, SYY is actually total sum of squares. How do we obtain this? It's actually summation of y minus the mean, and then we square. That's how you obtain, but in this case, we just use the given value. Alright, so the question is to perform the F-test to determine whether or not there is lack of fit of a linear regression function, and the significant level that we need to use is a 0.01. And then don't forget to conclude from our hypothesis testing. Alright, let us see the working or solution for the lack of fit test in order to perform the hypothesis testing. So the first step is we start to find the value of y bar and y minus y bar square in order for us to find the sum of square of pure errors. So the first step is to group the replicates, where replicates refers to the multiple measurements or observation. In this case, we group the replicates based on their x values, meaning that we are considering for similar x values, independent values. For example, the first one, we have the x that is equal to the observation 1. Let's say for the fourth group, so we have 4 replicates here. We have 4 same observation of x, so we group it together. The same thing for this one, we have observations of 2.0, so we group these replicates together. And then we arrange the value of dependent variable corresponding to each observation here. So from the original data just now, from the original example that we go through just now, so we just put or arrange the dependent variable, the observation of dependent variable corresponding for each x. And from here, we obtain the a mean for each group. Let's say for this one, so how to obtain this? So it's just calculating a simple average. You know, we sum up all the value and divide it by how many of it. So we have 4 observations, so you sum up all this and then divide it by 4, so you will have this value. The same goes to this. So here the next column is to obtain y minus y bar. So this value minus this value, and don't forget to square. So because this observation is similar, so therefore we have 0 here. Let's say for the fourth replicates here, so 1229 minus 1791.5, and then don't forget to square. Alright, so you get this value. So at the end, we will total these, and then we will have the sum of square of pure error. Remember, our sum of square of pure error is actually the summation of all this, and we have the value. So here, this is a degree of freedom. It's actually n minus 1, n referring to each group of replicates here. Let's say here we have 4, 1, 2, 3, 4. So 4 minus 1. That is why we have 3 here. So the sum of square of pure error, we already have the value. What about the sum of square error? Here is the formula SYY that is given previously. SXY also is given. Also, this is given previously. So we just substitute and then we obtain the value. And SS lack of square, sum of square of lack of fit is just you subtract the sum of square error minus the sum of square of pure error, and then you get the answer. And the F statistics can be calculated by obtaining or by dividing the mean of square lack of fit divided by mean of square of pure error. And don't forget, this is your degree of freedom. This is the n minus m, yeah, n minus m. N is your total observation. You have the 12 observations and you minus the, what is m just now? Our group here, so 1, 2, 3, 4, 5, 6, that we group all the replicates, so 6, and then mean of square lack of fit. Here, you take the sum of square lack of fit divided by the, here is actually m minus 2. So 6 minus 2, and then you will have the F test statistics. And after we have all the values, the next step is to perform the hypothesis testing. So you just write down the hypothesis. The null hypothesis saying that there is no lack of fit. There is for alternative, there is significant lack of fit. So the test statistics that you obtained before, mean of square lack of fit divided by mean of square of pure errors, 0.713. So this is your critical value. Don't forget the degree of freedom. So this is actually your m minus 2. Sorry, m minus 2, and here is actually n minus m. And you refer this, how to get this value, you refer your statistical table at in your F distribution. So we can have this value 4.53. So the decision rule here, since our F statistics is greater than the critical value, therefore we fail to reject the H null. We accept H null, in other words. So what we can say here, the regression model is linear, or normally we can say there is no significant lack of fit in the model. So meaning that our model fits the data well. So I've just shown you how to assess the lack of fit using the example just now. So we have another example, but I think you can try it on your own to increase your understanding on this lack of fit test. But we just go quickly on this example. Later you can try on your own. So this example is about the district sales manager for a major automobile manufacturer is studying car sales. He would like to know whether the number of cars sold last month is dependent on the number of full-time salesperson employed in the dealership. So this is actually your Y, I think. This is your X, right? So he randomly selected 15 dealers. So this is your number of observations, your N. From these dealers, he obtained data on the number of cars. All right. So given the same like just the previous example just now, we have the SXX, SYY, XXY. So we can just use this value to calculate sum of square error later, and then again perform a lack of fit test. So here is our significance level, 5%. Alright, so again, the first step, you need to group the replicates and then obtain all the, like the Y bar here, the average, and then you calculate this one in order to have the sum of square pure error. And then this is degree of freedom. Remember, this is like, let's say for this one, we have 4 observations. So this is actually N minus 1. That is why you have 3 here. Alright, and then you get the total here, 6. So this is the working or the solution. So just similar to the previous example that I've shown you just now. And we can also construct the ANOVA table for this lack of fit test. Instead of the same table or the regular ANOVA table, we will have additional component like the lack of fit here and then the pure error. Or the remaining component is just the same. It's just we have to add the lack of fit and also the pure error here. All right, and the rest is the same. You perform the hypothesis and then you get the decision, you obtain the critical value, and then you write down the conclusion for the hypothesis testing. Moving on to the transformation part. So in regression analysis, we often need to apply transformation to handle the non-linearity issue or non-normality issue in our data. So if we are dealing with the non-linearity issue, let's say our relationship between X and Y is not linear, so we can apply the transformation such as like polynomial terms, we add the quadratic terms, the log transformation, or it could be the power transformation. If we are dealing with the non-normality issue, we could consider to apply like log transformation, square root transformation, or even the box-Cox transformation. Alright, we go specific to the transformation for the case of nonlinear relation. For the case of nonlinear regression, when the distribution is approximately normal and constant variant, so the transformation on the independent variable x should be attempted. However, the transformation on dependent variable y may not be desirable in this case because the transformation on y, let's say the square root of y, it may change the shape of the distribution of the error terms and may lead to substantially differing error term variance. And we can also attempt to do several alternative informations. And don't forget to plot the scatter plot and residual based on each transformation, as we can compare which type of transformation is the most effective. Let's look at how we can handle nonlinear regression patterns using transformation. So as you can see here, the prototype here that we have is showing a nonlinear relationship between x and y. You can see that the data forms a curve, like for this one, which a simple straight line model cannot fit well. So for example, if we have this kind of situation, we can apply the common transformation known as log transformation. So we can linearize the data that like grows exponentially like here, and then we can transform the graph to show a more linear relationship, or we can apply the power transformation such as here, the square root, to stabilize the variance if we have this kind of situation and make the relationship more linear. All right, let's go through one example. So this data is about, it comes from an experiment on the effect of the number of days of training received. This is your X. This is your Y on performance in a battery of simulated sales situation. All right, so the question is to perform a square root transformation to linearize. We have to perform on the independent variable. Perform the square root transformation to linearize regression relation sales training example. All right. So before the transformation, we just obtain the regression equation. So before that, in order to have the regression equation, you have to obtain the slope or the regression coefficient for the x1. All right, here is the intercept or constant. So by using the formula that we have learned in previous chapter, so you just obtain before the transformation, I mean using the original data here, and then you complete this. All right, you can complete this, perform the square root on the x, meaning that here you have to find square root of 0.5, for example, until the last one, square root of 2.5. All right, after this, we will see how to compare before transformation and also after transformation by using the square root transformation. Alright, so we can obtain some plot before the transformation just to see the difference after we transform the variable, to see the difference before and after the transformation. Alright, so here are the some plots we obtain for before the transformation. For example, we have the plot of y, the dependent versus independent variable, and also we can obtain the plot of residual versus fitted value. This is the error, and this is the fitted value y hat. We can obtain this from our regression equation that we obtained in previous slide. So what we can see here, clearly the regression relation appears quite curvilinear. So the simple linear regression doesn't seem to be appropriate for this case. That is why we have to perform transformation for this data. So let us see the graph after we transform the variable. Alright, so here the plot that we obtain after the transformation where we apply or we conduct the square root transformation on the independent variable x. So here is a plot of y dependent variable versus the new x where we apply the square root. So we can see the line is a bit straight, linear compared to the plot before the transformation, and based on the normal PP plot, we can see most of the observations lies approximately close to the straight line, and from the scatter plot we can see like a reasonably linear relation between x and y. So this is the difference between before and after transformation. Alright, moving on to the transformation for the case of non-normality and unequal error variance. So normally, the case or the issue of unequal error variance and non-normality of the error terms, it frequently can appear together. So to fix this kind of issue, to fix these departures from the assumptions for the simple linear regression model, normally we need a transformation on the dependent variable y. So the transformation on y can help to linearize a curvilinear regression relation. But in certain cases, we can conduct simultaneous transformation, meaning that we perform transformation on x and also on y, on independent and dependent variable simultaneously to obtain a linear regression relation. Alright, now let's see some prototype of some issues or situations that require the transformation on dependent variable. So normally this involves the non-normality case and unequal variance. For example, here we have the case like the plot shows quite like a funnel shape here. So this transformation that might suitable for this case is by using the log transformation, or even if we have this kind of situation, we can apply the reciprocal transformations. So later when we apply this kind of transformation, we can plot to see before and after the transformation. Normally we can have better results, we can fix the issues by applying this type of transformation. Alright, so we have done on lack of fit test and also transformation. So lack of fit test is used to determine whether our model fits the data well or not, and transformation when we deal with non-normality, unequal variance, or non-linearity. So basically, here is the procedure for regression diagnostics. Once we develop a model, so we have to make sure the relationship is linear. So this can be done by draw a scatter diagram. So from the scatter diagram as well, we can find, or we can identify if there's any influential points, any outliers, or extreme observations. And then we determine the regression equation. So from there, we have to test whether the model that we obtain fits the data well by checking the assumptions, whether the assumptions are met or not. The assumption consists of whether the error variable is normal, the constant variance, independent, and if some issues occur such as non-normality, so we have to check, and if needed, we need to apply the transformations. So that's all for this chapter. Thank you for watching. See you in the next video.